So, good evening, everybody. So, I'm Naren, representing the School of CS and IT, head of the Department of BCA. So, I take this opportunity to introduce Ms. Haripriya S. She is actually an engineer plus plus in cyber, and she was also working as a senior software engineer in Peppo, First Walking Technologies, and so on. She is an AMCAD certified software engineer from Aspiring Minds, and she has completed her business English certificate Vantage level from University of Cambridge. She is a BTech in IT from Savita Engineering College, and the projects which she has carried out would include API health improvement as a project lead she has carried out, associated with Bank Bazaar India, etc. And she has also won a couple of awards in this field. So thank you for coming here, ma'am, to share your knowledge on the basics of data structures used in machine learning. Thank you. Thank you so much.
Yeah, thanks, Nari. Thanks for the introduction.
Yes, thank you.
Yeah. So maybe I'll start. I'll quickly share my screen and then we can start. Let me know if my screen is visible. Is my screen visible?
Yes, ma'am, it is visible, but we are not able to see this PPT or anything.
Yeah, I'm sharing it.
Oh, okay. Yes, now it's fine.
All right. Yeah, thank you. So let me just quickly start. So today we are just going to cover briefly about the data structures and some of the algorithms that are primarily used in machine learning. As I'm assuming that most of the students are already from the machine learning background, I just wanted to cover some of the important things which we need for machine learning, which is to know how to use the data structures, what are the available data structures, and what are the commonly or popularly used algorithms specifically in machine learning. So yeah, so today the agenda would be to cover the basic WH explorations, basically what, why, when, and how of the data structures. And we'll also be covering some of the popular data structures used in machine learning along with its examples. We'll also cover some of the WH versions of the algorithm and some of the popular algorithms that are used in machine learning with examples. Mainly one another thing is how to decide which is the best algorithm for your use case. Probably this is one of the things we always, I guess, get stuck to. We learn so much, but at the end of the day, we'll be confused on what to use for what use case when it comes to the application part. So we can, if not fully, we can cover some, we can get some insights and learnings about what are these and why it's more important in machine learning especially. So to start with, what is data structure? To just cut it short, it is an efficient way of storing and processing the data. So when we say efficient way of storing and processing, it means that anything we do in the machine, anything we do with the machine is basically to to interpret data. By the end of the day, it's just a ALU unit. It is just like zeros and ones, binary form of representation. So efficient way of storing and processing is crucial for any program or any logic that we write. So it is important that we learn and know what are the different structures that we got to implement. And similarly, that is the reason why I'll be using it as well for implementing a set of instructions effectively. And it's important to learn very much before we jump ahead and then learn the algorithms. Because the way we look at the data, the way the data is represented is the key before we even jump into logics. Because each of the use case will have its own data structure, will have its own. Like for example, let's say that we are into maps. We are looking into map data structure. We are looking into an image in the Google Maps, say, and in that. what kind of a data structure would be efficient? How do we represent the let's say lakes and lands and read and process it, right? So these are some of the interesting questions that we need to ask and then form a data representation before we jump and then derive a solution. And it's mainly used, as I said, for data analysis and data pre-processing stage. So before we write any core models for machine learning or for AI or for data science, the data analysis part, that is to classify the data or to understand whether it's a classification problem or regression problem, whichever be it. So that during that stage, we will need to, this data structure is more effectively used to represent the data in some form. And we will learn how to use it now. So some of the popular data structures, as we know, the machine learning arrays, sparse matrix, data frames, hash table, binary tree, and graphs. So I'll just add this before we jump into it. If you think that I'm very fast, you can stop me at any point. Like I'm not sure if I can see your hands, but you can just say hello or ping in case if you think I'm going very fast or if you didn't understand something. So yeah, to coming back, ML arrays. So ML machine learning arrays mainly vectors, tensors, matrix that we see are used in machine learning more often. So some of the libraries is numpy.nv array that we often use. Numpy is one of the very popular form of representing arrays when it comes to machine learning. So that arrays are like very commonly used that you do on a day-to-day basis. Sparse matrix. When you see any data with most elements as 0, then sparse matrix is effectively used. I will get into the details on why and when we are using it, but sparse matrix is one form of representing the data where when most elements are 0, you don't want to process them. You are saying that, hey, I know these are zeros. I don't want to keep looking into this particular point. Let me just look into the point which is important. So those are sparse matrix and scipy.sparse. Scipy is like a very popular library for data structures in Python that is used in machine learning. And for there is a library called scipy.sparse that is also that is mainly used for sparsing a given matrix, which will determine whether it's a sparse and will also remove those elements. We'll get into the details very quickly. And the next is data frames. Data frames is like a tabulated representation of a data, which you might understand. Pandas is like very commonly used again in machine learning. So yeah, data frames is one form. We'll also get into the details of how the data frames are being used, what is pandas, and what are some of the cool features of pandas, and how do we interpret them. So hash table, basic list, strings, and sets are like commonly again used. Hash lib, hash, and the very basic dict, if you DICT, dict, dictionary form of representation is also used in machine learning. Binary tree. So this is to understand the quick nearest neighbor lookup. So KD tree is something that is also popularly used. The reason why I'm putting all this is to get yourself familiarized with those libraries so that when you want to solve those problems, you are already familiar with the library and its use case. So yeah. So when scipy is as I said, that it has like a lot of benefits when it comes to a lot of additional libraries when it comes to manipulating a particular data. So it has sparse and it also has the spatial KD tree, which represents data in the form of a tree, such that it can look up the nearest neighbor. We'll get into these details shortly too. Graphs again. Undirected, directed graphs, hypergraphs, and everything. Matplotlib is like one library. Again, I'm sure that you guys might have heard. It's also like one form of a data structure for representing the data and also like viewing the data. Yeah. Any questions so far? Okay. Okay. So I will just move on. So popular DS examples, sparse matrix, as I said, like one form of a representing this. Let me just quickly show you some examples. So sci-fi.sparse, this is like one library that I do. So let's try to see what it does. Say if we just have a numpy array, this is going to be a two-dimensional array. So if we want to represent it, it can be represented as 001, 000, 102. Let me do this. 001, 0, and then again zeros. 0, 0, 0, 0, and then 0, 0, 2. If I'm not wrong, that is the data set. 1, 0. Okay. So here, how do we determine whether something is a sparse matrix or not? Right. So let's say this is a given matrix. You determine something is a sparse matrix or not when this has like 3 into 3, which has 9 elements, and half of it, let's say let's not say 4.5, but close 4 or 5 elements with zeros. So if the condition is met, then it is called sparse matrix. So in this data representation, it's clearly seen that we have 1, 2, 3, 4, 5 elements that are 0. So when we have matrices like this, we don't want to keep looking at the data that is 0, although we know it. Hey, I know it's a 0. I know it is a known data. Why do I have to keep looking into that every time I navigate the data set? So what you tell is, hey, just give me those numbers which has actual value. So you say that. So when you actually do a CSR matrix of it, you get these things. You get this as output. So what does it say? It says 1, 2 as 1. That is, in this 2D matrix representation, you have position 1, 2 as 1, and then 2, 0, 2, 0 as 1, 0, 1, 2. This one is 1, and then you have 2, 2 as 2. So this is like the more effective way of storing the data, right? You don't have to keep looking into the data which has element 0. So this is like one very popularly used data structure that can enhance the performance of the model that we are developing. So yeah, so the computational power is also increased, and because it's a 2D array representation, it is very easy. It is not that we need any explicit any other libraries or anything very specific. You can just go with any numpy array and then represent a matrix and determine whether it's a sparse matrix or not. This is like one popular DS examples. Second, what I wanted to cover is pandas. Pandas is mainly used for data cleanup. If you want to you have a huge data sets of millions of records, you want to clean up and then have only specific form of data, then pandas is used. You want to fill some data with junk values, like say, okay, I want a very balanced data set. I'm going to fill those that are unbalanced with a balanced data set. Then you use it. You use it for normalizing a specific data and inspecting it. We'll look into some of the ways in which we do it. So yeah, so pandas is one form of like I mentioned earlier. It's a data frame. I mean, data frame is like it's used in pandas. So data frame again, we saw that it's like a tabulated representation of something. So this is something that we can write. So we say that arrange 0, 20, which means it has 20 rows, and just give me the head. You can also say give me everything. 1 second to execute this. Okay. And then let me say if I do df, I have this. If I do df.head, I get like some parts of it. But anyways, we only have these indexes and columns that are represented in the data frame. So with pandas, what you can do, you can say, hey, access the elements of row 1, give me all the things that are there in row 1. You can say df.locate row 1, and it gives you everything. Similarly, you can tell what is the type of it, and here you can say that you can say give me everything that is located. Let me give you a better example of this. Yeah, if you say locate only the 3rd column, it gives you only the 3rd column, this one. And if you say locate everything, it gives you every column. And if you say locate only remove the first, and it will remove the first and then give you. Similarly, if you want to just get the values, you can still go ahead and give the values. So one another thing pandas is mainly used for is to read the CSV. Since you guys are already have implemented something, you have done this read CSV, right? So this is like one cool feature when it comes to let's say if you are going to use some other programming language like Node or anything, right? You don't have these cool libraries that can read the file and then just display the rows like this. So those of you who already have experience with other programming languages knows how cool it is to read a CSV just by pd.read CSV to read all the elements. And you also get the information of that particular data frame. When you do .info, you can describe it. You can count the values basically. So let's say that you want to count extend. Right. Okay, I have to now do this. Okay, I don't have the CSV. I believe I have deleted the CSV by mistake. But yeah, anyways, you can actually count the rows, you can count the head, and you can describe a specific the CSV values that are displayed. And yeah, those are some of the cool features with pandas. Those are anything else if I wanted to highlight? Yes. So you can actually do a re-indexing of a specific index as well. Yeah. Okay. This will be too complicated for the first time. But anyways, what I mainly wanted to cover is that pandas specially can play around with a data frame, a column row data frame. You can transpose it. You can you can mark something as null. You can invalidate a data. You can fill some values. Let's say that it only has A, C, E, F, and H, and then you are re-indexing with some new indexes here, and those values are null. This is one example of data fill. Similarly, pandas has like those features that are very important for that are very widely used in data structures. So when it comes to algorithms, we'll also explore some of the like basic ones to understand why we are using an algorithm and when to use it and all that. So algorithm, as we saw earlier, it's using the data structure that we have. It performs a set of instructions in a system to execute something. And why we are doing it? To efficiently execute it, such that the time and space complexity is minimal. For those who don't, for those who are not aware of time and space complexity, let's look at an example of, let's say you are looking at a data set that has n records, right? So if you have, let's say, a for loop here, I equals 1, I less than, let's say, 100, I plus plus. Okay, let's call it n cross n matrix. And if you're having a for loop where you're looping the rows, and inside that you're looping the columns again for j equals 1, j less than n, and j plus plus. Here you have to declare, for Python it's not required, for other things you have to declare I and j here. You have to, so what will be the time and space complexity for it? So the time is proportional to the number of records that we mentioned. Like say if m cross n is 5 cross 10, then as and then the number of records increases, the time is going to increase. So this is generally noted with a big O notation. So this is like so the time complexity is going to increase as and then we have more number of records. So as we write algorithm, we have to also ensure that you don't use too much loops or something. We have to write an algorithm effectively such a way that the time is almost on the straight line in a graph after some point. It can increase, we can have exception, we can have outliers, but we have to consider the number of inputs and almost make sure that no matter whether we process 10 trillion records or 10 records, the output is almost similar. The time at which an algorithm runs is the same. Similarly, space complexity. Space complexity here would be that we are using two variables here. Let's say we are determining some cost here. Cost equals, okay, if we are writing some logic here and we have we are returning cost. Let cost. So here we are, let me just do this down. So here we are allocating space for the variable cost, for I and for j, and for m and n as well, technically. So we are using more variables here to loop through and then determine something. So when such a program is executed, the system kind of allocates memories inside its processor. So the more space it takes, the more memory it's going to obviously take. So the computation becomes heavy loaded. So we also have to write an algorithm in such a way that the time and space complexity is always optimal. We can't always guarantee it's minimal, but sometimes the space is, we are taking too much space while writing the code. We are taking too much time. I mean, some programs might cost us too much time to run through, but we have to actually understand that when we write an algorithm, we have to write it in a way that the time and space complexity is optimal. And that's why algorithm comes in picture, where it is also important to know which algorithm to choose for which use case. So yeah, so when are we going it? When are we going for a specific algorithm, or when are we even writing an algorithm for use cases? As I said, when accuracy is very crucial, when each decision needs to follow the same process. As I said, whether it's 10 records or trillion records, we need an effective way of dealing with a problem. So how do we use it? We can use it. We can go through some of the popular algorithms that are used in ML. So one is greedy, and we'll go through greedy, Prim's algorithm, Dijkstra's algorithm, and Knn algorithm. So these four, if you go through most of the libraries used in ML, has these algorithms in place. Knn is very popularly used. Almost if you want to kickstart kickstart learning machine, kickstart doing some ML programming, Knn is like very often used. We'll go through what these algorithms are shortly to understand its steps. So yeah, so let me go through some of the algorithms. Let's take one greedy algorithm example. So what does it try to do? It tries to figure out the local optimal choice at each stage to derive the global optimum. So what does it mean? So greedy algorithm, let's say that we have trillions of ways to figure out the problem. It is not necessary that we have to go through everything every time. On a real-time basis, we can't keep going through every node to see which is the effective path or things like that. So at those times, when the data set is very huge for us to process, we go for this greedy approach. It's sometimes called as an approach, sometimes called as an algorithm, which is not very complicated. So one example is that let's take this take this person who is like a millionaire, who has like billions of 20 rupees, millions of 10 rupees, and millions of 5 rupees. Let's say given that the person has to give away 35 rupees, what are the different ways in which this 35 rupees he can give? Technically, he can do anything. He can actually have these 7 cross 5 rupees. He can give away 3 tens and 1 5. Like that, we have this factorial approach. But what is like the optimal way? What is like the greedier way for him to actually give away the thing? So how does it algorithm work? So the greedy algorithm looks in such a way that it first takes the highest. Greedy means that it takes whatever is the whatever is the highest possible number it comes across and puts it in the node. So at each stage, it tries to figure out. So in this example, it is the highest number. In any other example, it would be an optimal choice. Let's say that this greedy algorithm works in such a way that he has 20, 10, and 5. So he'll try to give 120, and then 20 is processed. Now it comes to the input, which is 10, and it takes 10 into consideration, and 10, and it tries to sum this up. The sum is actually 30, which still needs some more, which is still less than 35. So it looks into another input, another choice which is 5, and here the 30, and the sum comes to 35, which is 35. But this is not a very optimal approach though, and it cannot be applied for all use cases. Let's say that he needs to give away, let's say 50 rupee, 53 rupees, right? So he does not have 3 rupees as such in place. So how does he give out things which he does not have it as an input? Or let's take one more example which will fail for sure. let's say you are in the middle of a road, a blackout road, where you don't have where your target is to figure out a goal. And each block you traverse, you get number of goals in each of the blocks you travel. But you don't know where to go because everything around you is dark. Let's have blocks like this, right? Sorry. So let's say the value of gold here is 0, 1, 3, 4, and then here maybe 1, and here maybe 2. Let's say you're starting from this position. Let's say you're starting from this position. Let's see. Let's take 3. Let this be 7 actually. So let's say that we are going with the greedy approach for it. You are in a dark room. You are trying to traverse. You are taking a greedy algorithm approach. You all you see is only the neighbors around you. You have 2, 3, and 1, and then you take a greedy approach. Go here, so you get the gold 7, and then you don't have any other path. So in the greedy algorithm, one another approach is that once you have taken the path, there is no way of going back. So you have to keep going in that path. You do 4, 3, 1. So 7 plus 3 plus 1. So the sum is 11. So you only get 11 goals. But if you had you taken this path, you would have ended up with 12 goals here. So greedy algorithm need not necessarily be an optimal choice for all use cases, but it is like an algorithm that we end up at some stage where we don't know where to go. We have like no idea how to follow. You just take one approach, at least you derive at a solution. Otherwise, you land nowhere. Let's say we have like millions of possibilities of traversing. You really can't traverse each and everything at a given time and then try to figure out a solution. So greedy algorithm works in such a way that at least at some point I derive at a solution and be contented with it. So that's one algorithm. Prim's algorithm, on the other hand, I'll stop here and maybe if you guys have any questions, I can clarify. Otherwise, I can go ahead.
How did we get that 11 goods there? I mean, like, we have traversed from 4, 3, 1, right?
Oh, sorry, my bad. My addition is bad. So this is 8.
Yeah, that's all. Okay.
Yeah, thanks for pointing that out. Yeah, so it is 7. It is 4, 3, 1, and 8, and here you have 12. So yeah, so the idea is to just understand we will not anyway end up with a optimal choice every time we take up this greedy approach. Thanks for pointing out anyway. Okay, so next is Prim's algorithm. Prim's algorithm has like a similar approch to the greedy algorithm, but it is that it works in the concept of minimum spanning tree. Sorry, someone was saying something?
Least weighted edge.
Yes, exactly. Least weighted edge. So how do you determine the least weighted edge at any given time? So how do you traverse is that?
We select a small path. I mean, like the small weights and then sum up it.
Exactly. But to start with, we can start with any node at
any verticism. Yeah, we can select anything.
So let's say we take a node A. We take a node A, and then we traverse through this node. to derive at the minimum. We can say it's the shortest path, but it's the minimum spanning path that we are trying to determine from one node to another node. So this can also be used for shortest path algorithms at some time, but not necessarily every time. So yeah, so if you guys are like already aware of Prim's algorithm, maybe I can. Is everyone aware of it already?
Yes, ma'am. We have this in our academic part.
Okay. Okay, then I'll skip. So Prim's algorithm, I just wanted to highlight this. I don't want to go through each and every stage of this, but ultimately it is an algorithm. It is also most of the. It's an algorithm that's also mostly used in our machine learning approaches. One example of this would be again maps. In maps, let's say we are given a use case of. Let me give you a use case. So the real-time example would be that you want to, let's say, see you have X and C's of a map. You have the representation of X and C's representing land and water, right? At any given point, what is the minimum spanning? Using, I mean, this is one of the implementation of the minimum spanning tree, but the use case would be, let's say, at any given point, what would be the what would be the possibility that you start in the land and end in the land, and you don't jump in the water. So this is like one of the examples of a Prim's algorithm used in real time. And for which, I mean, this is widely used. Distras is also widely used. I hope you guys are aware of Distras as well. Is anyone aware of this? Okay, I'm assuming that this is not covered. So Distras is also a shortest path to arrive at the node, but this works in such a way that you actually you go through each and every node to determine. So basically, you try to derive what is the shortest path of one node to a given node. Like you traverse through every node and then try to determine, let's say, what is the shortest path to traverse from S to A. Then what is the shortest path to traverse from S to C? Is there even a path to traverse? And if yes, what is the shortest path to traverse from S to B? So like that, you try to determine the shortest path of one node to each node. Another good example, similarly in maps, where you try to, like most of the Swiggy use cases, Swiggy or Zomato, or even in our Google Maps use case, where you try to determine traveling a distance from one to another. Let's say if it's going to take 10 minutes to travel from A to B and 20 minutes to travel from A to C, like that you have a data, and then you try to determine what is the shortest path given at arriving at the given node. So we can go through this example quickly without explaining any of the other use cases. So how this Dijkstra's algorithm works is that, so we have explored nodes and unexplored nodes. So we take two segregation in place. So in the start, everything is unexplored. A is unexplored, S is unexplored, B is unexplored, and C is unexplored. And we are going to say that, we know we are going to start with one node. So traveling from the same node to, it's traveling from S to arrive at S is going to be 0. But the other nodes currently, they are unexplored. So this is going to be, so this is infinity. Okay, sure. Thanks, Shravan. Yeah. So this is infinity. This is also infinity. In the initial phase, we haven't explored any of the other nodes. So here, so we'll go through the nodes one by one. So we haven't explored. So we'll start with the node S, and we will say that S is traversed. At this stage, it will be just this. Just give me a second. Yeah. So this will be 0 and nothing else at this stage. We are going to retain this, saying that only S is explored. And here, what happens? S, A, B, and C. So at this stage, traveling from S to A, how long does it? I mean, what is the weightage of it? It is 1. So you say this is 1s, and then traveling from B to S, it is going to be 3s. This is 3. This is 1. Then we have explored S now. Then we'll go and explore the second one. So second one would be A. We know that A is 1s. So we are going to take that in consideration, and we are going to see. And we are going to see how long does it take for us to reach B. So here so the Distrast works in such a way that we will take the minimum path at every explored stage. So B already has 3s, but from A it only has 1. So we are going to do 1 plus 1, which is 2s at this stage. And the rest, we are going to retain the same, because we will explore only one node at any given time. And this, at this stage, we will have B and C. And B, this is not 2s, this is 2a. And B, we have 2a, and C, we have. So at this stage, we will just keep it like this, and then we will, okay, yeah. From S, can we actually traverse to C? Yes. How do we traverse? 1 and 10. So it is going to be 11B, 11A. So again, we are going to consider these, and then take C. In here, to traverse C, we already have 11, but we have B node. From B, can we traverse to C? Yes. Then what is the minimum path that it takes to traverse to C? This is 4, and we already have 11, so we are going to consider this 4B. So yeah, I think we have covered all the nodes, so we are going to stop here and say that S to S will be 0, S to A will be 1, S to B will be 2, and S to C will be 4. So this is one another shortest path algorithm. One of the techniques used, as I said, in our Google Maps, Swiggy, Zomato, everything almost popularly uses this Dijkstra's algorithm only on a day-to-day basis. That's one popular. Next is Knn algorithm. This I'm not sure if you guys have covered before. Let me know. This is also like one of the widely used algorithms in machine learning. Okay, I'm assuming that it's not covered. So let's take an example of let's say a group of people. You already have a data set of group of people who are traveling to China for a marathon, say, right? So you have people arriving from different countries, different continents to land in a specific place in China, let's say region. So you are given this data set to train, and you are asking one of the Chinese people to predict the continent they are arriving from, given a distance. So if they have traveled 2,000 kilometers, then predict the continent they are arriving from. They have traveled 10,000, then predict it. Like that, you wanted to predict a specific continent of a person, given that this distance and this direction. So if this is going to be a use case, then the KNN is one good implementation for determining this, problem, solving this problem. So how this K nearest neighbor works is that it uses the principle of Euclidean distance. Euclidean distance is, let's say you have two distances, A and B. So at any given point, to travel from A to B, I think minus. Okay, let me just say it's Africa, because I've given the example as Africa. I've written that as Chinese. Okay, so any given 2 points, how do you determine the distances? You use a formula for Euclidean distance. Let's say this is the point x1 comma y1, and this point is x2 comma y2. So how do you determine the distance between 2 points? Is you actually square x1 y1 and some x2 y2, and then figure out a square root of that to determine the distance. This is like a very popular Euclidean distance formula. This is like one of the classification problem, right? So in this particular example is a classification problem where you have the data set classified as North America, South America, Europe, Asia, and people like this, and then you are trying to determine from which continent they are arriving from. So the K nearest neighbor works in such a way that it looks for the shortest distance that is from a given point, and tries to determine from which continent they are arriving from. I think I'll get back to the China example itself. Okay. So let's say that you have a point here. This is your x1 and y1, and you want to determine from which continent arriving from. Looking at this graph, you can easily say this is the closest point. They are from Africa. So you are predicting that most likely the person who is traveling from a given point must be from Africa because they are closer to Africa. How do you do it? You try to determine the distance from a given data point. You already have a data set for this to all these are plotted, and you're saying that, hey, I know all these regions are Africa. Anything closest to it is going to be Africa. So how KNN widely works is that, so if the K value is going to be 1, what is K value is? K is the nearest neighbor, one nearest point that you are considering. Let's say you are considering Africa. If you are going to consider one nearest point, then what are the nearest possible values you have? Africa. North is like very far, and Australia is also far. So it is easier to determine this point is from Africa. Similarly, red K2. Okay, K1 is you are drawing one line. One line nearby is Africa, so you are going to say Africa. K2 means you are drawing 2 lines. What is the next nearest? Africa, then Australia. But Australia is again far, so you can know that this is from. You can still conclude that it's Africa. Let's say the K value is 3 for the given point. What is the next nearest? Maybe north. That is also technically far. When I say far, this distance is something that you are computing with Euclidean distance. When you compute it, this is also far, and still you stick with your answer that the person is from Africa. This is one example. But what if the points are elsewhere? What they say that there are 2 cases for this. One is one we call outliers, where the point is almost outside the range. So here, let's say we have a point which is not even in the range. It's somewhere here. You have this extended, and it's somewhere over here. It's somewhere over here. So no one is nearby technically. You can still say maybe he's from Australia or Africa, but still the point is like very far off. Maybe if you put the point somewhere, somewhere here, it's very far off, and we call these as outliers. And these data points these are like the drawbacks of KNN as well, because this will still determine the Euclidean distance, right? But you won't be able to derive from where the person is coming. The person can still be from Africa. The person can still be from Australia. Maybe with the Euclidean distance you can figure out, but there is no conclusion. There's no way, the range is nowhere nearby. So this is like one drawback of KNN. Let's take one another example, this purple dot, right? Okay, let's take this purple dot. So what happens in this purple dot? If you are putting a point here and trying to determine distance, both Africa and Australia are equidistant. So K1, if you're going to just put one distance, it can still be Africa / Australia. If you're going to put K is equal to 2, then it is still Africa / Australia. You have like confused, you are at a confused stage here, because both are giving you 2 possible results. So what do you do at this stage? Usually they say for KNN, one key thing is that always go for odd numbers. It might still not work all the time, but it is usually said that always go for odd numbers, such that we are always left out with one extra data point that we can evaluate with. So if we are going to take one more and then say, hey, I'm going to do K as 3. Here what happens? You have you have Africa, Australia, and you're going to consider Asia as well. Even at this stage, you still arrive at a confusion between Africa and Australia, but you for sure know that they are only two data points that you need, from which you need to determine. There are no other equidistant values that you have, that you can ignore other, you can ignore other features and then say, hey, most likely between Africa or Australia, that I'm sure. So yeah, this is like one algorithm that we use for finding the nearest neighbor, and it's very popularly used in machine learning as well. So yeah, I'll pause here. Maybe you guys can ask questions if you guys have anything. Yeah.
Yeah, any questions from the student side? You can please ask. Students, you have any questions, you can please ask, no? Otherwise, I'll ask on your behalf. I can also ask, no, Haripriya ma'am. I'm allowed to ask, right?
Yeah, sure.
Okay. Students, any questions?
I have a question.
Yeah, Joe, go on.
How do you know when to use which algorithm? Like,
Okay, yeah.
uh,
Good, thanks for pointing that out.
Good question.
I wanted to cover that, but I was. Thanks for pointing that out. Yes, that's one very important thing. I'll show you an example. Okay, let's take the nearest neighbor example itself, right? Here I have just written down an example of k nearest neighbors. When to use when is how do you know what algorithm is to use is you will know it when you are trying to represent the data in some form, and then you filter out the algorithms that you can never use it. So one way of knowing which algorithm to use is one way of knowing which algorithm to actually get rid of. So that can be determined by visually representing whatever data structure that you have. So here, let's say that you have this. I've taken one example of a classified data set from a company. I just took it from Kaggle. So we'll try to use Knn in this example here. I have a classified data.csv. It has about, I think, 10,000 to 20,000 records. I'm just displaying a head. Most of the data set that you get, right, usually the features are, on a real-time basis, the features are like blocked out. So what they will mostly give us you a target class. So from that, it is almost impossible to actually know what algorithm to use when you do not know how to actually classify and represent the data. So what is the use case of this is that you need to create a model which predicts a class for the new data. Which predicts a class for a new data point based on the features. So at any given point, if you say, hey, what is the let's put it this way. It's like the same algorithm. So this is target class 1 and target class 0. So if I say a point, to which target does it belong to? Can I actually draw a line and say, is it that simple? Or what to do? I have like different classes like this, 0, 1, 0, 1, 0, 1, like this. So at any given point, let's say if this is going to be a point for us, then what is the target? Then what is the target class of this point? That is the use case. What algorithm do I use if my data is like this? But even to understand this, how my data is represented, you need to visually see the data. So how do you actually go step by step is to first see what are the heads, You remove these index call 0. You don't need this, and you display the head, and then you standardize it. Why is standardization important? Because it can fall under any category, right? Sometimes this can be the value 12. You don't know what it is. So you want to standardize it into 0 to 1, maybe. If you can standardize this data into a specific representation, then you can plot the graph. So one of the very popular method for standardizing data is standard scalar. So I'm standardizing the variables here so that it comes under -0 to -1. So that's the -0 to 1. So that's the representation I'm making here. And then I'm pairing the plot. So there is this library called Seaborn. This is used for visually representing your data. So this Seaborn pair plot, you're saying that, hey, use the target class. That is this 1s and 0 is going to be our end feature. So use this target class and try to plot the data. So if you look at the plot, the data here, if you see, there are too many overlappings here, right? Lot of data are overlapped. So how do you actually classify this data? Do you actually go for a regression or a classification? Is it a regression or classification problem? Itself is a question mark here. So you can't draw a line and say, hey, the data falls under this and this line. You can't draw a line like this or this. So linear regression or logistic regression, everything is ruled out here. For sure, the data is overlapped. Now, some things that you can think about is maybe it is a random forest, maybe you can use decision tree, maybe you can use KNN. The decision tree and random forest, it's going to take too much of trial and error, and it's going to loop on, because for each node you need to decide whether it falls under 0 or 1 at every stage. But most of the data are overlapped. For these kind of a problem, KNN is a very go-to approach for most of these problems where the data is overlapped. So
Okay.
yeah, so if you use KNN, at any given point you determine the Euclidean distance and then try to classify the data.
Okay.
I heard, yeah. So you train and split the model, and then you try to predict with the K value. So choosing the K value is also very important. Let's say that you choose the K value as 1. So when I choose the K value as n neighbors as 1, the precision here is 91 to 89, good enough. I choose the K value as 23, the precision is again good enough. So I know that this model will work for most. Here, for example, I used first 40 samples. If you see here, I use the range 1. Of the whole data set, I use the range 1 to 40, which might not be very optimal choice, but you need to go through all the records and then try to determine the K value. If for most it is positive, the precision is good enough, then you can use this model to determine a specific data point for you. I heard.
Okay. Sure. Thank you.
Sorry, I heard something. Let me just open it. Yeah, sure.
Yes.
Yeah.
So it was a good question, and thanks for answering, madam.
Yeah.
Yes,
Thank you,
students
ma'am.
can fill the survey form also here, which is here.
Yeah, sure.
You can take just a few minutes and fill. Any other questions from the audience? We'll just take one or 2 minutes. Okay. I think I assume that there are no questions.
Okay.
Yeah, thank you, Haripriya ma'am. It was a wonderful session. Like you had started from the grassroots level of what is machine learning and what are the data structures and how to integrate it. So it was a beautiful session. Even a beginner could follow. So thank you so much for taking your time amidst your busy schedule and coming here and giving a session. So on behalf of School of Engineering and Technology and School of Computer Science and IT, JAIN deemed to be university, I give my hearty thanks to you.
Yeah.
Thank you so much. Thank
Yeah,
you so
thanks so much, Naren. And thanks, students. I had a good time interacting with you.
Yes. Thank you. Thank you. Thank you here. Same
Yeah.
here.
Yeah.
Thank you, madam. Thank you. Thank you, students.